Okay, hello everyone. Welcome to this video where we're going to look at graphs of logarithmic functions. As we've discussed in previous exercises, a logarithm is just the inverse of an exponential. So a great way to go about this is, let's start with a reminder of what an exponential looks like. Find its inverse, graph an inverse, and then we can start to identify some patterns that there may be. So let's just start with a nice easy sketch of f of x equals 2 to the x. So a quick reminder, we cannot get f of x in this case equals to 0. Okay, doesn't matter if we let x equal to 0, well, anything to the power of 0 becomes 1. We put -1 in there. It doesn't matter what we do, we cannot get f of x equals to 0. In other words, we're saying we cannot get y equal to 0. So from that, straight off the bat, as a reminder, we have an asymptote at y equals 0. Okay. Rolling on from this, a great way to start is to get an intercept. So let's just let x equal to 0. So it follows on f of 0 is equal to 2 to the 0 is equal to 1. So we get a point there, 0, 1. And then let's maybe do 2 points of reference. Okay, so let's let x equal to 1. It follows on f of 1 is equal to 2 to the 1 is equal to 2, which is there. And then we'll let x equal to 2. So we get f of 2 is equal to 2 squared is equal to 4. So up there. And then if we did at -1, we'd get a half there to start with. So we get 1, 2, and we get 2, 4. Okay. So the graph of f of x looks something like that. Just a reminder for what a graph of an exponential looks like. Okay, it gets big quickly, really quickly. Okay, if we substitute in just let x equal to 4, okay, let x equal to 4, we get f of 4 is equal to 2 to the power of 4, which is equal to 2 times 2 is 4, times 2 is 8, times 2 is 16. Okay, so by the time we get to this point there, we're up at 16. So off the page. So it gets real big, real quick, and that gain increases. Okay, so that is a reminder. So let's continue on. Like I said, let's find the inverse. Okay, so we had f of x is equal to 2 to the x, which we could call that as y equals 2 to the x. To find the inverse, we switch our x and our y. So we could say this is equal to 2 to y, and I'll just put in the little -1s to show that we're working with an inverse. Okay. Now, how we know we could use our shortcut log rule. So that, say if we had y equals a to the x, we know it follows on that log base a of y equals x. Okay. We could use this pattern. Okay, we can transfer backwards and forwards between this. Okay, but if we want to do it the long way just to show, okay, we could take log, in this case we'd take log base 2 of both sides. So we get log base 2 of x in this case is equal to log base 2 of 2y to the inverse. Now, using log law, we can say that we can take the y to the -1 out the front, so we get log 2 x is equal to y minus 1 log 2 base 2 of 2. Now log base 2 of 2, that is asking 2 to the power of what gives me 2? Well, it's just going to be 1, so we get log 2 to the x is equal to, that needs to be, I've written that a little bit wrong. Y to 1. We're talking about the inverse of y. We get the inverse of y. Okay, so we've just found our inverse. So this takes us back to point C. This takes us now on to question C. Given the inverse of an exponential is a logarithm, sketch the graph of f to the -1x on the x provided on the first slide. Okay, so we know that this log, okay, is the inverse of the exponential. Okay. So when we have an inverse, okay, going back to this first one, inverse is we're effectively swap our x and y coordinates. Okay, if you were just given data points, okay, and you said plot the inverse of it, you could just switch all the x and y coordinates. So let's just start by doing that, and then we'll see what the sort of shape looks like. So instead of 0, 1, that's going to convert into 1, 0. So we get a 1, 0 there. 1, 0. 1, 2, that's going to convert into 2, 1. So we're going to have that there. So 2, 1. 2, 4, that's going to convert into 4, 2. Okay, we can keep following this pattern. We could do this for every single data point. So even this point here, we know that that is -1/2. So we could switch that again, and we're going to get half -1, which is there. Half -1. We could do that with every single point on the line, and we're going to get a graph that looks like that. That's going to be our log graph. And with this, okay, a special thing to note is we get a new asymptote. Our asymptote is changed. And our new asymptote now is x equals 0. And to double check, and we can sort of see this reflection if you remember back to when we first looked at inverses. Inverses will reflect about the line y equals x. Okay, so we can see that black line flipping over y equals x is now our green line, the inverse of it. So there's our graph of, and I should probably label this is f of x, and this is the inverse, which is the log. Rightio, so that's a quick demonstration of what a graph of a log looks like. We have a vertical asymptote. Okay. The equation still gets, or the line still gets bigger and bigger and bigger, but in a much, it gets large in the x now, much quicker than it does in the y. Okay. The range, to be clear, our range is still, our range, y is all elements of real. Okay. Our range, we go all the way down to -infinity. If we kept going on long enough, we made x big enough, y would still keep going up. Okay, goes up slowly vertically for a log, but it still goes up. Okay, so let's find the inverse of these. Okay, so we're going to just start by switching. Remember that pattern, so we get x equals 5 to the y, and I'll put my little -1 to indicate that we're dealing with inverse. And we should just start to rearrange, so we get x plus 2 equals 5. Okay, so we can use our log exponential conversion, okay, or the equivalence. So this would turn into log base 5 of x plus 2 is equal to 1 order, right, in the other order we get the inverse is equal to log base 5 x plus 2. F of x, okay, is equal to log 2 of x minus 1. We could rewrite this as y equals log 2 x minus 1. We can switch our x and our y, so we get log 2 y dash minus 1, inverse of y, not y dash, sorry. inverse of y, and now we start rearranging. So to rearrange, we're going to end up with 2 to the power of x is equal to the inverse of y minus 1. So we get the inverse of y is equal to 2 to the power of x plus 1. And now, quick thing to confirm is that we were given this in terms of f of x. So there's no y in this question, so we actually need to instead say the inverse of x is equal to 2 to the power of x plus 1. You need to give it in the correct variables that we were given, or term, okay, in the question. Right, so just like in exponential graphs and pretty much every single type of functional relation we've looked at the moment, transformations can be applied to logs. Okay? So when we sketched exponential, we saw we had a horizontal asymptote. Now, as I showed in that previous example, logs, we have a vertical one. Okay. Other than that, the process is exactly the same. So let's have a go at this. Sketch the graph of y equals log base 3 equals x, including asymptotes and intercepts where they're present. Okay, so let's find our x-intercept first. Nice place to start. So we'll let y equal to 0, follows on 0 is equal to log base 3 of x. Okay, we can write that as 3 to the 0 equals x, so x is equal to 1. So that gives our x-intercept. Let's try and find our y-intercept. Okay, so y-int, let x equal 0, it follows on y is equal to log base 3 of 0. So then we get 3 to the y is equal to 0, and that is not possible. 3 to the power of anything cannot be turned into 0. Okay, so that's not possible. So that is actually asymptote. Okay, at x equals 0. So like we said before, we have a vertical asymptote, and this one is occurring at x equal to 0. Let's put in our other point, which we found before, which was at y equals 0, x equals 1. So we get 1, 0. And so we have that. And I would also find a point of reference. Find a point of reference. So in this case, I'm going to tactically let x equal to 3, and I'll come back to why I've technically chosen that to find this point of reference, but it will make our life much easier. So we get y is equal to log base 3 of 3. Y would be equal to, this log is asking 3 to the power of what is equal to 3, so that's going to be 1. So y is equal to 1. And that gives us our other coordinate, which is 3, 1. Right there. So we've got 3, 1, and we have 1, 0. Connect the dots. And our graph looks like that. Okay, excuse my not very well curved drawn line, but you get the idea, get the gist of it. Okay, so a couple things to note out, and I actually will cover the domain really quickly. The domain, x is an element of real positive. Okay, or we could say x is greater than 0. Or we could say 0 up to positive infinity. Any of those ways describe the domain. Okay. X needs to be greater than 0. Let's go back to my tactic of letting my point of reference and letting x equal to 3. Why did I let it x equal to 3? If we go back to the log in here, and I'm picking this 3, okay, by letting let's call, what will we call? Let's call this blue box. Okay. By letting the blue box equal to the base, okay, of the log, okay, it's always going to be something that we can solve without a calculator. Okay, so if we choose an x value that makes the box equal to the base, so this, in this case it was log base 3 and I just had an x, okay, that's going to be something that we can always do in our head, because it's going to be asking, in this case it was 3 to the power of what equal to 3. It's always going to give us 1. So if we follow this strategy of choosing an x value, so effectively we're going to choose x so the box is equal to the base, we're going to get a nice simple log that we can solve in our head. So that's one really good strategy. Ooh, my apologies. The other really strong strategy that we'll know is that the asymptote, okay, asymptote occurs when that box is equal to 0, because it's asking us to try and get something. So in this case, 3 to the power of something is equal to 0. So there's our two really strong strategies, okay, or tactics or techniques for helping graph log functions. So let's give that a go. Okay. And you always have to try and find intercepts. Okay. So sketch the graph of y equals log to the base 3 of x plus 2, including any asymptotes and intercepts where they are present. So very first off the bat, let's try and find our x-intercept. So we'll try and find our x-intercept. So that's let y equal to 0. It follows on that 0 is equal to log base 3 of x plus 2. So we get 3 to the power of 0 is equal to x plus 2. So 1 is equal to x plus 2. So we get x is equal to negative 2. There's our intercept. Now I'm going to put my blue box in here that we talked about. Okay. And we're going to find our asymptote. Okay. So our asymptote, okay, is when our box is equal to 0. So it follows on that we let x plus 2 equal to 0, so we get x equals negative 2. Silly mistake in the previous one. 1 equals x plus 2, solve that, that's x equals negative 1. Okay. So our asymptote is x equals negative 2. So if we could try and sub that in quickly to double check. Let's put it in. So I put negative 2 in there, I get negative 2 plus 2 is 0, so I'm being asked 3 to the power of what gives me 0. That's impossible. So it is therefore an asymptote. So let's sketch that in, what we have so far. So that's x equals negative 2. And we also had a coordinate point at negative 1, 0. So there, negative 1, 0 is our point. And the last bit is my point of reference, and we're going to be tactical with that as well, like we mentioned. Okay, I'm going to make my box, okay, equal to the base, so that's going to be 3 this time. Okay, so we'll let x plus 2 equal to 3, so x is equal to 1. What am I doing? I can use my, x equal, therefore x is going to be equal to 1. Yep. Okay, so let's do that now. So let x equal to 1, it follows on that we get y is equal to log 3 to 1 plus 2. So we get y is equal to log base 3 of 3. So, and we get this situation that we wanted. 3 to the power of what gives me 3. So in this case, it's going to be y is equal to 1. So we get our second coordinate point at x equals 1, y equals 1, which is right there, 1, 1. So this was really tactical in that this bit over here, okay, highlighted by the red around it, you can start to do that in your head. Okay, you can look at, okay, what do I need to make x? What do I need to make x so that everything in the blue box is equal to 3? Well, it's quite obvious that I need to just let x equal to 1. So I'm going to choose that as my x coordinate for my point of reference. I was just showing full working. So in this case, we've done that. Okay, I'm going to just pick x as 1, substitute in, and it's giving me y equals 1. We have our 2 points of reference, so we can do that. Okay. Now we have something missing. We're missing our y-intercept. Okay, so running out a little bit of space here, so I'm going to just have to work up the top. So for our y-intercept, x is equal to 0. It follows on that y is equal to log base 3 of 0 plus 2. So we get y is equal to log base 3 of 2. And I wish I had my calculator with me right now, because that is something that need calculator for. Let's see if I can do this on my calculator on my phone, but I think it's about 0.68. Okay. That's going to do log base 10 of it. Oh. Sorry about this. Poor preparation. Base 3 of 2. Yes, 0.63. So we get 0.63092. Keeps going on and on and on. But 0.63. Will be close enough. Same thing with our domain. Okay, x is greater than -2. Or -2 up to positive infinity. Okay, let's go again. And this one I will go through a bit quicker, but the same sort of process applies. So that x-intercept, let y equals 0, so we get 0 equals log base 3 of 2x. So that's the same as 3 to the 0 equals 2x. So we get 1 equal to 2x. So x is equal to half. So our coordinate point is half 0. Right there. Okay. Put our box around log. So asymptote will be when box is equal to 0. Therefore 2x is equal to 0. Oh, I've drawn that in completely the wrong spot. Oh my god. Half 0. Okay, so x is equal to 0 is our asymptote. X equals 0, and we're not going to have a y-intercept, So we're going to do a point of reference. So I'm going to let my box equal to 3 because that's what my base is. So it follows on to x equals 3, so x is equal to 3 on 2. So if I substitute that in, I get y is equal to log 3 of 2 times 3 on 2, and this is, we get our pattern that we want, that the 2 and the 2 are going to cancel out, so we're left with y is equal to log 3 of 3. So 3 to the power of what gives me 3? Well, of course, y is going to be equal to 1. So we get our coordinate of 3 on 2, comma 1. So 3 on 2 is a half, so I need a bit of space there. Okay, so we've got our first point was half 0, and this one is 3 on 2, 1. Like that. Yeah. And there we go. Okay, our domain again is x is greater than 0, or x is the element of real positive, or from 0 up to positive infinity. Okay, and that's it for exercise 13G, which is graphing of log functions. Okay. I hope those strategy here of thinking about, I guess, this box, okay, whatever's in the log, choose x so that is equal to our base when we're trying to find a point of reference, and our asymptote will always occur when that box is equal to 0, and that'll give you a way to find your x value for the vertical asymptote. Any questions, like always, ask in class or through Compass or Edmodo.